So we are studying lectures on p-divisible groups written by Michel Desmazur. So this is a lecture notes of Michel Desmazur. Actually, it is a book. It is a published book. Lecture notes in mathematics. The number of this book is 302, published by Springer. We're not claiming any copyrights. We just use it for self-study, so I do not use it for any commercial reasons. Okay. So chapter 1, schemes and formal schemes. Chapter 2, group schemes and formal group schemes. Chapter 3, with groups and Dieudonné modules. Dieudonné modules, very classical objects used to classify p-divisible group over some perfect rings, let's say. Chapter 4, classification p-divisible groups. And there are many things later. Actually, it's a generalization of Dieudonné module, I think. For example, things display. There are many other linear algebra things used to classify p-divisible groups. But the motivation, I think here is a motivation why we use Dieudonné module, why it is possible to use linear algebra to classify p-divisible groups. The last chapter is p-adic homology of abelian varieties. You can imagine maybe for a given abelian variety, we know the p-torsion points. We form inductive system, which is a p-divisible group, and we can study the p-adic homology of this p-divisible group. Maybe we will see later. Okay, let's come to the first chapter, schemes and formal schemes. This is an approach. It's not in the way we're familiar with to define scheme and formal scheme. It's not in the way we saw in Harshon's book, topological space, into with a sheaf. Here is the equivalent approach. It's in the factorial view. Actually, of course, at the beginning it is more restricted and precise, mainly focusing on the affine case, but it is studying the scheme by the unida embedding, which is fully faithful. We will say that is to say that to regard a scheme as its representative functor. So for scheme, we associate its representative functor, which is home in the category of maybe schemes over some fixed base or not. Like this. So this is a functor from the category of schemes. Maybe we write some restriction here to the category of set. This is a unida embedding, and it is fully faithful. In that case, we do not lose information. We'll see precisely what is going on. Okay, let's go. So the first point is key factors. Let K be a ring and MK be the category of K rings. So it's commutative associative K algebra with unit, or simply couples R and phi, where R is a ring and phi is a morphism. It's just to mention that it is firstly commutative, secondly with unit. Okay, it's firstly commutative associative K-algebra, secondly there is unit. Actually, for set theoretical reasons, we should not take the category of all K rings, but the smaller ones. We shall not bother with this. The key functor is by definition covariant functor from MK. We call the notation MK is category of K rings. Okay. If you want, we can use a notation like this. Because K is a ring, usually we don't use small k, right? We use R, but we know what we're talking about. So let's don't bother with the notation. Let's keep the notations we saw on this book. Key functor is by definition covariant functor from this category MK, so the category of K-algebras, to the category of set. The category key functor is denoted by MKE. Those notations are very old, it's not very easy to be reminded what it is, but let's just do it slowly. Example, the fine line OK, and the line is defined by this. So this is a functor. It is a functor from the category of K rings, the category of a set. This is the key functor, which for any object in this category, it is mapped to R itself, but it's regarded as a set. For beneath R to S is arrow, is phi is an arrow of MK, so it's a ring homomorphism. And if X is a functor, and if small x is an element of XR, we shall write small x, or sometimes small x instead of this. So this is just to light the notation, okay? Make the notation light. Instead of x is a functor, instead of write like this, we are just to write this, or just small x, without abuse of notation, without confusion. If f is an arrow in the category of R ring, so it's a ring homomorphism. No, sorry, if f is arrow in the category of functors, so if f is a natural transformation, which means that for example, there is phi R to S, then you have XR, XS, FR, it's natural transformation, R, phi, Y phi, YS, FS. You will write again FRX. Instead, we just write fx. Okay? And the commutativity This diagram, which amounts to the definition of f is natural transformation, now become what? Combined with the notation we use above, so fx, we map down, we map to fx, small s. And here when you first map down, it's small xs. And we mapped here is f, small xs. And these two are the same, give you the commutative. The category MKE has projective limits. For example, a final object E is defined by an empty set. If big X and big Y are two functors, the product is defined by, we evaluate on some object, because it is functor, evaluate on some object, it is the product of their image, because X and Y are two functors. Okay, so we define it in this way, which tells that the product exists. And then the third one, if here is a diagram, the fiber product is defined in this way. So we constructed the fiber product defined in this way, and we define projective limit of key functor in this way. We evaluate on key algebra R. It equals the limit. So this limit is taking the category of a set. Okay, so it's always exists and modified. The fourth one, F is a monomorphism. So this is in the category of key functors. It is a monomorphism if and only if for any object. This is the definition, okay? For any morphism, this one is injected. It's because here is in the category of set again. Or maybe by definition, monomorphism, when composed with some object, when composed with some morphism, the two morphisms are the same if and only if the two morphisms we compose with are the same. Maybe this is result, and because this is a functor from category to set, maybe you can directly derive that this is not a new definition but consistent with what we had. We see that X is a subfunctor if the image is a subset. And so a subfunctor corresponds to a morphism, because you have to require that FR is the inclusion. So this morphism make all the image inclusion. That key prime MK as any key prime algebra can be viewed as a key algebra. There is an obvious functor and therefore an obvious functor. So firstly, what is M key prime? F key prime is key prime algebra, key prime ring, sorry. If key prime is in MK, it means that key prime is a key algebra, key ring. So by composition, this is the obvious functor. So this is a functor, from functor to functor. Okay, so MKE is, what is it? It is functors from MK to the category of set. And as we mentioned, there is arrow from MQ prime to MK, and so the composition gives the MK prime to E. So given a natural transformation here, by the composition we get the natural transformation here. And we denote this functor. This is not a ring. X is a functor. This is very formally written in this way. This is a functor. What is this? Here's the definition. Okay. In other words, if you write x here and this functor here, we denote by x tensor. But what does this mean? It means that for any object R here, we map it to R is mapped to this, and you compose with x. This is the notation. This is called the base change functor or scalar extension functor. It commutes with projective limit, hence is left exact. Small exercise to check that it commutes with project limits. Simply speaking, so if you have a system, disregard the notation. You have to check. I take the limit, then evaluate. By definition, you will say it is first take limit for this functor, and then apply the composition. Finally, evaluate. In general, we know for left exact, this is not the equivalent definition in general. Precisely, I mean that a functor is left exact, it's not equivalent, it commutes with projective limit. More rigorous speaking should be remark: if f is a additive functor between two abelian categories, which is not the case, then f commutes with finite projective limit. And then leave f is left exact. This is sketch. Let's recall sketch proof. This is a homological algebra, sorry. So if f preserves zero object, finite product, pull back, then F preserve projective limits, finite projective limits, sorry. If F is left exact, remark that F is left exact implies that F preserves pullback. So if F is left exact, then F preserves pullback, and if F commutes with finite product, and it's additive, it preserves zero object. Sorry, I have to mention that this is additive function. And from this, we know this is always true. It preserves product. And F is left exact implies it preserves pullback, because pullback is some kernel constructed. It is a kernel of constructed morphism. Okay. And so together this implies for additive functor, left exact implies preserves finite product limit, and conversely, if F preserves finite product limits, finite projective limits, sorry, then one can show that it preserves curves. Kernel, sorry, what am I saying? Kernel. And this will imply that F preserves. F is left exact. For example, take an exact sequence. A preserves kernel tells you that this is injective, but it's not obvious. So this position is also exact. But we know that preserves kernels will tell you that image A equals kernel F, apply F, image of F A equals just of this. We have F of kernel F equals kernel of FF. This isomorphic to F of image A equals kernel F equals image A. So F of image A, so F of A isomorphic to kernel of FF. So this is again exact. Second section of fine key scheme. At A, the K ring, the key functor, denoted this way, SPKA or simply SPA is defined by, so this is again functorial way, yes, and we evaluate on R. R is again a key ring. This is inside set, which means the home in the category of K algebra, K ring from A to R. This is in the category of set, object in the category of set. This is really like the home functor. Okay. To be more tidy, this is in its category. So this is really the functor is this, right? In its open category. It's representative functor. And for morphism, fine. This functor maps home RR to home SR. How is the map? Sorry, I written wrong. It's not R, it's AR to AS. A is fixed. Because there is already a map from R to S, and if you have A to R, then this is a composition to have A to S. Compose with phi. If F is an arrow, then this is obviously defined. This is natural transformation of two functors. From HB to HA, okay? HF. So this is contravariant functor from the category of K-rings to the category of functor. This is really the representative functor. You need that functor. And affine K scheme is a K functor isomorphic to some HA. For instance, OK is an affine K algebra because it is, what is this telling us? It is H KTR. Because KTR is K ring. This is really as a set bijection. One thing to remark: home as K algebra. Just that fixed image of D, but that's a K module. Because K is just a ring, it's K module. What is this? Just preserve 0 and you can map 1 to anyone you want. But again, it's K algebra. What is this? Just one element. What is pi? Pi is the structure map. Which means that pi is, when you say R is a K ring, you mean there exists actually. Maybe it's better to denote it. Denote pi R, pi A, or pi R is like this. More consistent, okay? Let X be a K functor in the A K ring. We have the very simple and very important unida bijection. The in the bijection is, it's easy to it's really same as unit dilemma. We can look at it by diagram, which makes things more simple and tidy. For me, I'm really writing this way: S P K A. R is whatever R you want. For this Frobenius map from A to R in this category, of course. Where is phi come from? It's because by definition. Right? This is it. Actually, we want to define this. We are claiming that to determine this, it's equivalent to determine this. Say there is bijection into an element of this set and element of this set. What is element of this set? Element of this set is a natural transformation functor. In other words, for any R in this category, okay, you have to tell me what is this map of sets. So I am telling you, for any object in this set phi, I'm going to tell you what is the image. I'm going to tell you that to determine the image of any element of this set. In other words, to determine a map of this is for any given R is equivalent to define an element of this. Let me write down more precisely. When you choose phi here and you apply the functor SPK A to this morphism, what you get is SPK A to A, which is home, A to A, map to home, A to R. And you know this map is by composition, so you compose identity with phi, so identity is mapped exactly to phi when you are applying this functor to this phi, and here it's the same. Identity is mapped to some object here, let's call it Xi, and then Xi is mapped to what? Still applying this functor X to this morphism, so it's mapped to X phi acting on Xi. Just tell you that the image of phi is known. If the image of identity here is known, so you see there is bijection between element of XA and image of phi. And we say once you fix C, you know all the image of phi for any phi of this set, and not only for this set, for any other, for any R and any element of SPKAR, you know the image. So you see the bijection. This is the Nida bijection. And this is fully faithful. And when you take, for example, because here x is any k functor, we don't know it's affine or not if you take. But if you take a affine SPKB, then you see this in that embedding is more or less like that. More common. Representative functor here in the category of k-rings, k-algebras. This is what we really saw, what we really come up with. This fundamental equivalence can also be looked at in the following way. Let x be a k functor, define functor on x to be a morphism, a functorial system of maps. A function on x. Function on x is for all r. Okay. You collect the arrow. Okay. This is the same a map of functor. Natural transformation. I'm not right equal, right? Bijection, okay? The set of these functions, say OX. Right. When you collect this, you denote this OX. Sorry, it's not. OX is the set of these maps. Those F's has a obvious keyring structure. What you find at this moment is just a set, a function. When you define it this way, it becomes a ring. For any object keyring, XR is a set. We took our element inside it and we fix it by the very definition of the keyring structure of OX. OX is telling you how to sum to function on X, how to multiply to function on X together, how to do the scalar multiplication. So therefore have canonical morphism. Sorry, this one is an element. SPOX here is evaluated on R, which is by definition O from OX to R. So for any f of OX, this is a map on X. I can, if you have prefixed the element of XR, then f valued x. Recall this definition, this notation. F is a natural transformation is from x r to okay r, which is r, and if here you fix small x, this is mapped by our notation. We just denoted fx, but we know fx is in r. Okay. We therefore have canonical morphism from x to SPOX. Intuitively, what is this telling us? OX is like the coordinate ring of a affine scheme X, and so this is the isomorphism for a affine scheme. How to say this is a universal map. So let's write down. Any other morphism? Factor through alpha. So you have to show there is a unique error like this. Write that more precisely. So what we need is construct arrow from A to R, A to OX, making this diagram commute. So this arrow is already clear. Map small x to a map which maps f to fx. You really have to construct this arrow and you see whether it commutes. So fixed element small a in big A, I map it to element of OX. So it's a function of X, which means that for any element of X valued on some object B, you have to map it to some element in B. What is the choice? What is the canonical choice? Suppose this is phi, I'll map this to phi x, so it's in here, phi x. And you can evaluate on an element of A, give the element of R. Sorry, so here is R. This is again, because phi x is a home from A to R. Evaluate on it, this is in R. So this is indeed a function on X from XR to R. And of course you can change R to whatever you want. Just notice that phi is not for fixed R, it's for any R. Phi is here actually. Right? The factor is like this. So you can evaluate on any B if you want. And what do you map to? You map to phi x. A, finally it's inside R. No, sorry. So here's composition. So the last step is from OX to R is, as we said, for a given map. If you know this F, and this is just Fx. In particular, in this case, what is Fx? Fx is phi x A. So once this diagram commutes. This is in algebraic geometry. What does this tell us? What does this tell us? This tells that morphism of scheme into a affine scheme factors through the affine scheme of its coordinate ring, of its global section. So X spec OX has a bijection with now this. It's like this, right? X is an affine key scheme if and only if alpha is isomorphism. For instance, this is the key functor we have seen before. This function over it is polynomial algebra KT, generated by the identity morphism. It's really like this affine scheme. The functor commutes from A to HA commutes with projective. It's not HA. When you evaluate on K-algebra, it is HA. Yes. Commutes with projective limits and base change, but has the following obvious isomorphy. So someone may ask question. The category of K-algebra is made inductive limit. I think here is inductive limit, it's not just co-limit, which means that the inductive system will assume it is a filtered system. This is just the commutative algebra argument. We have defined the fiber product of key functors before. Here we have defined the tensor product of a key functor before also. You have to just check both sides are well defined. You have to just check it's true.